And now we are perfectly on time to move on to our next speaker, Barış Çakmak from Bahçeşehir University. He's a young, brilliant scientist and received several important awards, including Mustafa Parlar Award from METÜ. And Barış is working on, in general, open quantum systems. And recently, he shifted his interest from quantum optics to a little bit more fundamental questions in quantum thermodynamics. And he's also an expert in general on quantum control theory. And we look forward to listen his lecture today. So Barış Hocam, whenever you like, you can start your lecture.
Thanks a lot. Can I have one more request? Can you, so there's also another participant named Barış Çakmak tablet. Can someone also make that a co-host so that I can share my screen? Okay, thanks a lot.
Okay, this has been taken care of.
Okay, it should be fine now. So, okay, I guess you can see the page at this point. Everything is fine, right?
If possible, it might be better to make it landscape, right?
Landscape, okay, hocam.
Yeah, this is much better. Thank you.
Okay, thanks a lot. So thank you for the kind introduction in general. So today I will be talking about thermodynamics of quantum control, but mostly I will be talking about controlling closed quantum systems. So there are actually three words in our title. So we have quantum. We have thermodynamics, and we have control. So there are so all of these. So you can group these three words in groups of two. All of them make sense, basically. So we have, so I'm in general, as Özgür just stated, I'm in general working in a field that's called quantum thermodynamics nowadays, which basically deals with the definition of heat, work, entropy production, irreversible entropy production in non-equilibrium quantum processes. What do I mean by this? I mean, the following, for example, I deal with problems involving driven quantum systems. So quantum systems that have that we have an external control over, such that we can drive their Hamiltonians at a finite time or in a designated time interval. So it's interesting to see what happens in this case, the amount of irreversibility that we create due to the finiteness of the process, or we can also investigate quantum properties such as coherence, correlations on the thermodynamics, on the thermodynamic properties of these systems. So we have so these two. So quantum thermodynamics by itself is an emerging field, basically. Maybe thermodynamics of control is something that we are maybe we are in general not familiar of, but actually when we talk about thermodynamics or when we talk about thermodynamical processes, what we usually want from such processes, what we usually demand from some thermodynamic processes is we in general would like to identify processes that waste the minimal amount of resources. Therefore, we in general, I mean, when we analyze thermodynamical processes, we in general want to control them in a way such that we waste the minimal amount of resources. So, I mean, this is by itself something meaningful, so thermodynamic control in that sense. I mean, you can also historically trace this back even to the beginning of the thermodynamics, which is basically due to Carnot, Sadi Carnot. And I mean, the science of thermodynamics actually emerged through the analysis of making better and better engines in the beginning of the Industrial Revolution. So I mean, so the wasting minimal amount of resources basically is at the core of the thermodynamics. Now, finally, the quantum control part is something that's actually, I mean, relatively new, I would say. Because, I mean, in general, so there were a couple of, I mean, people already mentioned this a couple of times yesterday. So we are, so it's a classical word to say that, okay, we are in the beginning of this, of the second quantum revolution, which is basically attributed to a paper in the beginning of 2000s, written to Proceedings of Proceedings of the Royal Society, I guess. I will put up all the references in a Drive file at the end of tomorrow's lecture, so I will also put that paper in. So the second quantum revolution basically refers to the following. So the first one was these computers, these electronic revolution, let's say. So in this first revolution, we were basically in a passive role. So we used the tools of quantum theory to understand the properties of materials, such that, I mean, we built devices out of them. So we understood that the energy levels are discrete. We have these kind of things. So we took advantage of these things. So the second quantum revolution basically refers to a phase in which humans are expected to have a more active role, such that they actively manipulate quantum systems to basically do tasks, perform tasks such as information processing. I mean, quantum computing also enters into this information processing title. And also, we would like to build like devices, thermodynamic devices, quantum counterpart of the thermodynamic devices. So in this case, we basically need quantum control. We need to control quantum systems as they evolve from one state to the other. Okay. So this is in general the main motivation. I mean, I didn't need to give the title in Thermodynamics of Quantum Control. I might as well given the title as Quantum Control and Thermodynamics, or any other combination. So basically, let's try to start from somewhere. So we basically, in a general, a central task in physics, and also maybe in engineering also, is we in general want to control, we want to take an initial state, and in the end, if we are going to perform a task such as an information processing task, a computational task, or a thermodynamic task, whatever the task that we want to do, we take a physical state and we basically want to manipulate it according to our aim. So this is this is a central task. So we want to transform states from an initial state to a desired final state. Okay, this is a very general problem in that sense. So so a central task in physics, like we can say state transformations. Okay, so we would like to start from an initial state, let's say, I mean, counting on the lecture of Ceyhun Hoca yesterday, I am lucky that I can freely use these state vectors, Hamiltonians, and expectation values. So we start from an initial state, let's say psi initial, okay? And then I want to evolve this to a final state, psi final, okay? And then I would like to, in general, while doing this, I change a parameter in the Hamiltonian of this system. And the Hamiltonian of the system is basically an operator that's controlling the total energy of the system. So in general, I have a time-dependent Hamiltonian in which I have a parameter that I can control such that this state is transformed from an initial to a final state. Obviously, during this time evolution, this time evolution itself is in general described by the Schrödinger equation, the time-dependent Schrödinger equation, which we can write as IH bar, the time derivative of psi H psi. Oops. Okay. So that's fine, but the problem stems, we come across a problem when we want to basically do this state transformation at a finite time, okay? Because, I mean, again, let's refer to a thermodynamical concept. So any finite time process irreversibly produces entropy, okay? And this irreversibility is quite problematic because we, in general, would, as I said, we would like to waste minimal amount of resources. So when there's an irreversibility, it means that we, so it's literally, I mean, as the name suggests, it's irreversible. So we waste some amount of our resources into that irreversibility. So we lose resources. So, so maybe let me write this. Any finite time process irreversibly produces entropy. Okay, and this entropy is something that we cannot trace back to a heat exchange. Okay, so it's like an intrinsic entropy production due to the finiteness of the process. We will, I mean, in detail refer to this in a moment. Okay, so therefore we usually, so in order to waste minimal amount of resources again, we usually perform such transformations in quantum systems adiabatically. Okay, what do we mean by adiabatic? We mean the following: we perform these transformations. Usually, we perform these transformations very small. Özgür Hocam, you want to interrupt?
Yes, maybe you can clarify if you exclude unitary processes, no?
Unitary processes in what sense?
Because the unitary process wouldn't produce any entropy.
Yes, it would conserve the von Neumann entropy, but in general, when you perform a unitary process at a finite time, you would generate coherences, right? So it would create entropy production, even though not entropy. So in that sense. So in general, we usually would like to evolve a system infinitely slow in that sense. So we would like to resort to adiabatic dynamics. So in general, adiabatic processes for quantum systems. Now, for quantum systems, adiabatic processes, as I said, are infinitely small. In fact, the adiabatic theorem itself, quoting from the original paper, itself, which introduces the adiabatic theorem for quantum systems, it states the following. And so a physical system remains in its instantaneous eigenstate if a given perturbation is acting on it slowly enough, and if there is a gap between the eigenvalue and the rest of the Hamiltonian spectrum. So what we mean by this is that if we change the control parameter in the Hamiltonian of our system slowly enough, and if there is an energy gap, so assume that you are in an eigenstate of an Hamiltonian, and you are changing the Hamiltonian. If the energy state that you are in have a well-separated energy level from the rest of the spectrum, and you change the parameter in your Hamiltonian slowly enough, then you remain in this energy eigenstate, so that you can control. You can change the state of your system under control without causing any irreversibility in that sense. Okay. However, as I said, these processes are infinitely slow, depending on your energy, depending on your separation from the rest of the energy spectrum, and depending on how fast you are doing this. So, I mean, in order to be in the adiabatic limit, you need to perform this process in a very slow manner. Okay, so these are slow processes. Okay. However, we do not have that much time with quantum systems, especially because the quantum systems are inherently fragile. What do we mean by this? I mean the following. So any quantum property would be lost with an inevitable interaction with the environment. Okay, so any quantum superposition, any quantum correlation between if you have a multipartite system, any quantum correlation would then also be decaying as the time goes by. Therefore, you would prefer fast transformations. Okay, so quantum systems are inherently fragile. Therefore, fast manipulation is required. Okay, now this is where the quantum control part comes in. Okay, so people thought about some ways to overcome this this slowness of these adiabatic dynamics, which provides us a high degree of control. Okay, even though they are slow. So the name for these techniques is called shortcuts to adiabaticity, and many of the quantum control protocols can be considered within this umbrella of shortcuts to adiabaticity. So shortcuts to adiabaticity. So this would be the main title that we refer to when we talk about quantum control techniques. So there are a couple of different techniques, as I said, that goes under this name. And what they do is, you can imagine they are doing something like this. So they take a slow process and they basically put some wheels on it so that this turtle can move fast. Okay. So we take these adiabatic dynamics. We desire and we want to be in control of our quantum system while we change some of its properties. It's better to do this adiabatically, but it's too slow. So what we want to do is basically we would like to find a shortcut to these adiabatic dynamics. Okay. Now there are a couple of ways that you can do it. One way to do it is basically to remain as you move from an initial state to a final state. You remain on the adiabatic limit at all times. So some of these shortcut techniques does this, and some of these shortcut techniques that probably I will not have the time to talk about. What they do is that they do something different as you move in between the initial state and the final state, but they guarantee you that you end up at the adiabatic final state. Okay, but in the meantime, between initial and final states, your state leaves the adiabatic limit and goes to other states. But the control method basically guarantees you that at the end of the process, you will be in the adiabatic final state. So how does these shortcuts to adiabaticity methods work? They usually work in a way, in the following way, basically. You have your Hamiltonian, h of t. You have a parameter that you can change in this time-dependent Hamiltonian, okay? So an STA method basically does the following. So if you change your Hamiltonian slowly enough, you will remain in the adiabatic limit and everything would be fine. But if you would like to hasten this process, what you do is you basically take your Hamiltonian and add an external control Hamiltonian to this. So let's say HSTA, okay? Depending on the type of the shortcut method that you would like to apply, the form of this HSTA changes it. Actually, okay. So today I will be talking about one STA method, which is basically quite central in these, and quite central and quite popular within this shortcut methods, which is basically the counter-diabatic driving, or it's also known as transitionless quantum driving. Okay. In order to do that, I will try to, I will basically go through a very simple derivation in which we are only going to use the eigenvalue equation for the Hamiltonian and also the Schrödinger equation. I will not even solve the Schrödinger equation. I will just write the differential equation for the Schrödinger equation. Okay. So that we can see what a finite time driving can do to our system, and how can we get rid of that effect by adding an extra control term. Okay. Let's maybe let me maybe put the title counter-diabatic driving here. Okay, So I will, at the very end, we will reach to this expression for the counter-diabatic driving. But for now, let's say that we have a time-dependent Hamiltonian, okay? So we have a time-dependent Hamiltonian, okay? H of t, okay? And then it has a set of eigenstates, instantaneous eigenstates. And by instantaneous eigenstates, I mean the following. This Hamiltonian is changing as the time goes by. It's a time-dependent Hamiltonian, clearly. And these eigenstates also follow these changes, because since the Hamiltonian is changing, the eigenstates of this Hamiltonian is also changing, okay? So let's say that I label them with n. So these are also time dependent, and they are the instantaneous eigenstates. So they satisfy this equation, En of t at all times, okay? So the set of these eigenstates N of t, they are denote the instantaneous eigenstates. Okay, fine. And let's say that we have the following initial state, which basically is composed of, which is a superposition of these instantaneous eigenstates. Okay, so we have the following initial state. Okay, let's say psi, or not an initial state. Okay, let's say that we have, let's not call it the initial state, but let's say that we have a state that is basically in a superposition of these instantaneous energy eigenstates. Okay, and now we know that this state, which is in a superposition of all the instantaneous energy eigenstates, it evolves according to the Schrödinger equation. Okay, which basically tells you that IH bar, the time derivative of psi of t, is equal to ht psi of t. Oops, sorry. Okay, so we can basically just plug this in, okay, and see what happens here. So I'm going to drop the time dependence here, but please keep in mind that all of these things are time dependent. I'm just dropping them to have a more compact notation, okay? So when I plug this in here, I need to take the time derivative of the right-hand side. So I have a time-dependent coefficients, and I have a set of time-dependent eigenstates. Okay, so I need to take the time derivative of both of these guys. Okay, so I have an IH bar. Fine, I'm keeping it. And I take the time derivative of this Cn. So I have the summation over n. So I have the time derivative of Cn, and I have the eigenstates. Okay, plus I have Cn and the time derivative of the eigenstates, because they also depend on time. Okay. Fine, and on the right-hand side, I have the following. So I have the Hamiltonian that's acting on my state psi. So my state is Cn times n of t. Okay, and remember, these n of t are the instantaneous eigenstates of the Hamiltonian. So when the Hamiltonian basically hits to these n's, it will spit out an En, basically. Okay. So I am going to have, again, sum over n, Cn, En, n. Okay. Fine. Then let me do the following. So since these instantaneous energy eigenstates form up an orthogonal basis, so they are all orthonormal to each other, in fact. So let me approach this equation with bra m from the right-hand side. Okay. Now this would give me the following. So this m. So the first term that it would come across is this n. So m and n, they are always orthonormal to each other. They only give 1 since they are orthonormal when m is equal to n. Okay. So as the first term, I have I h bar cm dot and m and m will give me a delta function, which is basically 1. And as the next term, I'm going to have an IH bar here. Okay, I have a sum over n. Okay, I still have Cn here. So I have n dot here, and I'm coming with an m. So I don't know the result of this, so I'm going to keep it as it is at this point. Okay, and on the right-hand side, I will also, so if I hit with m bra m from here, I will also hit this with the same bra m. So it would again give me, so this, out of this summation, it would pick when n is equal, it would pick the term when n is equal to m. So this would give me Cm em. Okay, and that's the only thing. So let me, maybe if you like, I can rearrange these things by simply taking this guy to the right hand side. Maybe it would be much better. Okay. Okay, and then I am going to make this a minus sign. Okay, so I have the time derivative on the right hand side, and I have time derivative of the coefficients on the left hand side and the rest on the right hand side. So from this sum, let me separate that separate the term when n is equal to m. Okay, so from the sum, separate the term n equals m. Okay. Now, what would I have when n is equal to m? I am going to have minus IH bar Cm m dot. Okay. And let me group this Cm with this n equal to m term here. Okay. So I have an IH bar Cm dot, which is equal to like Em. From the n equals m term, I have a minus IH bar, m dot, okay, in the parentheses. So, and then I have the Cm parentheses here, okay. And the last term is IH bar, the sum when n is not equal to m, because I separated that term. And then I have Cn m and dot. Okay. Now this is basically the expression that I would like to reach. Okay, so let's try to analyze this, or let's try to make sense of this. So let me remind you what the adiabatic theorem stated. Okay, a physical system remains in its instantaneous eigenstate. Okay, if a perturbation is acting slowly enough, let's keep it there. We have a separated energy we have a separated spectrum, so I don't need to refer to the next part at this point. So a physical system remains in its instantaneous eigenstate if a given perturbation is acting on it slowly enough. Okay, so so Cm is the coefficient of an instantaneous eigenstate. Okay, remember. So I'm going to, so Cm dot is related to Cm if I can get rid of this term, okay? So if I am able to ignore this term, okay, the time derivative of Cm will only be related to the Cm, okay, which is basically my my coefficient on that energy eigenstate. So I do not have any coupling in this if I can ignore this term here. So this term is the problematic term at this point, okay? So if I can ignore this term altogether, I do not couple to any of the other energy eigenstates, okay? So it already hints you from this expression that when can you ignore this term? So if, as you can see, if this n dot is small, okay, or even if it's not changing at all, okay, if n is not changing at all, n dot would be 0, so we would get rid of this term here, okay. So if the Hamiltonian is not changing, we are fine if it's time independent. Or if this n dot is small so that I can neglect this term, I'm again fine, okay? So because this is the term that couples me to the rest of the energy eigenstates, okay? And it does this in a non-controlled way, right? So, I mean, when the last term is negligible, last term is negligible, I only have Cm dot equal to this quantity times Cm, okay? And then this would be a trivial first order differential equation. So Cm would be given by an exponential of minus I h bar integral from 0 to t prime, let's say, Em minus IH bar, sorry, M dot dt prime, okay, with Cm 0 here. So the value of our coefficient of the energy eigenstate would only depend on the initial value of that energy eigenstate, okay? So this is basically the adiabatic evolution. Okay. Again, I'm repeating when we can ignore this last term, which means that when n dot is small or 0. Okay. So so I will tell you in a moment how can we get rid of this term, but maybe it would be instructive to see what this term is, m n dot, okay? So try to understand m n dot, okay? So in order to do that, let's remember that this eigenvalue equation, these n's are the instantaneous eigenstates of this Hamiltonian H, okay? Now let me take the time derivative of this equation here, okay? Let's say this is star. Differentiate star with respect to time, okay? Now, what would I get? In this case, my Hamiltonian is time dependent. So the derivative of the Hamiltonian times the eigenstate plus the Hamiltonian itself times the derivative of n, which would then be equal to En dot n plus En n dot, okay? Again, let me come with an orthonormal bra from the right-hand side, okay? So from this first term, I would get m h dot n, okay? From the second term, so this Hamiltonian is a Hermitian operator, as you all know. It can operate to the left and also to the right. So when I come with m from the left, h can operate on this m and give you a em, okay? And this is m, this is n dot, right? And on the right hand side, so en dot is just a number, so m and n, they are orthonormal, so they would only give 1 if n is equal to m, okay, which is not the case, so this term drops down, and then as a final term I would get en m n dot, okay. Now let me rearrange this. So this term, so I was curious what this term stands for, m and dot inner product, remember, okay? So let me leave that alone. So I have an em mn dot, en mn dot. So let me leave m and dot alone. I would get the following thing, okay? So m h dot n, this is a matrix element of the time derivative of the Hamiltonian divided by en minus em, okay? Now this tells us quite a lot actually. So the term that's causing the problem here, not the whole thing, I will come to the whole thing in a moment, but just this single thing, m and dot inner product. It's basically dependent on the time derivative of the Hamiltonian, which basically is a measure of how fast you are changing the Hamiltonian, okay? And also it's inversely proportional to the energy level separation, okay? So the energy difference between two different energy eigenstates, okay? Now, if you are varying your Hamiltonian very slowly, which means that this h dot is very small, then this term is small, which means that we can neglect this last term here, and we are in the adiabatic limit, okay? And also pay attention to the fact that this term is inversely proportional to the energy level separation. So when the separation is high, when the energy level separation is very large, this term is again very small, okay? Which basically also relates to the second part of the adiabatic theorem, if there's a gap between the energy eigenvalues. So when you don't have any gap, or if the gap is too small, you would again be easily out of the adiabatic evolution or the adiabatic limit, okay? Fine. Now, let's write the whole term, okay? Now, so let me conclude somehow by saying a couple of things, okay? So clearly, when h dot is small, we are in the adiabatic limit, okay? Or, okay, I can add a term to my original Hamiltonian h of t, okay? So to my Hamiltonian h of t, I can add a term that after all these calculations that we went through, okay, cancel this term here, okay, cancels this term here. Now it basically comes with an minus IH bar, the sum over n not equal to m, Cn m n dot, okay. Now what I can do is that, or I can add the positive version of that term, or add the following term to your original Hamiltonian, okay, which is, let's call this as the HCD counter-diabatic or H transitions driving, which is IH bar, the sum over n not equals to m, this term here, m h dot n divided by e n minus e m, okay? So that this HCD, when you add HCD to your original Hamiltonian H here, you would get rid of this last term here, and you would be in the adiabatic limit, no matter how fast you change your Hamiltonian, okay? This is called the counter-diabatic driving. So this is a quite general result, okay? So when you, you can do this for any Hamiltonian you like, okay? And this allows you, this counter-diabatic driving allows you to perform any finite time, allows you to remain in the adiabatic limit for any finite time process, no matter how fast you do the driving, okay? However, the problem with this term is the following, which I will probably be talking about tomorrow, is the following. So the first thing that's, the first problem, which I won't be talking about tomorrow, probably is this. So when you have small systems, for example, when you have a two-level system, a qubit, or when you are talking about a harmonic oscillator, problems that can be easily solved, finding this HCD is quite easy, okay? However, when you have a many-body system, as you can see, we have M and N here. So these are the instantaneous energy eigenstates of the Hamiltonian. Don't forget that, okay? So you need to know these things, and you also need to know the energies of these instantaneous energy eigenstates as you are changing the Hamiltonian, okay? So to calculate CD, you need to know these eigenstates and eigenvalues at all times, okay? So for a qubit, this is doable. But for a many-body system, for example, for 50 qubits, 50 spin 1/2 particles, this is an intractable problem. So applying this counter-diabatic driving approach to many-body systems is a bit problematic. There are ways to overcome this. Maybe I can very briefly touch them tomorrow. And the other problem is that so this is an additional Hamiltonian term, okay? This is an additional Hamiltonian term that I need to introduce externally, okay? So I need to do this thing that I did at the top. So if I would like to do an STA to this Hamiltonian H of t, this H of t, I'm going to add an HCD to this, okay? And this is an external thing, okay, that I need to do. Basically, this is what we mean by controlling the quantum system. So I, as a person or a person in the lab, I need to somehow apply this counter-diabatic driving. So this is going to have an energetic cost, okay? That's also a bit problematic in some applications of these counter-diabatic driving, because you need to decide if it's worth energetically, if it's worth to do this counter-diabatic driving, or in fact do everything slowly such that you remain in the adiabatic manifold throughout the dynamics. So this is where the thermodynamics of quantum control comes in. So the energetic cost of this term is also quite important, and finding ways to reduce this cost is also important. Maybe I can stop here and then continue with a very small application and the cost discussion, and how this cost comes in, how it comes in in different applications of these counter-diabetic driving and why it is important in different applications.
Thank you, Barış. I'm sure these step-by-step derivations were very clear and helpful to the students and everybody. We can take some questions, but maybe let me do the opening. So at the beginning, Barış, you said that you want to design some control method to get some initial state to a target final state, right? So this is the basic problem. And now we just designed this AHT to do this, but we realized that this is fast and we want to increase the speed and add this HCD. And how do we know that we can still get the same target state? Will we end up somewhere else?
I mean, the thing is, so if you know that, so this depends on the Hamiltonian, obviously. So you basically, I mean, I was planning to do an application, but maybe it would be more clear when we do an application, for example, a Landau-Zener avoided crossing type of application. So in general, you imagine an idealized process in which you know that when you change a parameter in the Hamiltonian from an initial value to a final value. So let's say that during this transformation, I have a parameter lambda, okay, in the Hamiltonian that's time dependent, okay, and throughout this transformation, I change this lambda from its initial state to its final state, lambda final, okay. Now, in this idealized process, if I imagine this idealized process and then I say that, okay, if I do this adiabatically, if I vary this slowly enough, I would end up in this final state that I desire. Once you can say this, once you fix these parameters and all, depending on what your desired final state is, then you can count on the counter-diabetic term to make sure that you end up at that final state. So you think in an idealized world that, okay, if I do this adiabatically, I would end up in this state. Once you fix this, once you conceive this idea, then the counter-diabetic driving term basically does the job for you, as if the dynamics is adiabatic, but with the help of this HCD, we do it at a finite time. But the faster you do it, the higher the cost, the energetic cost of this counter-diabetic term, but that would be the topic of tomorrow, probably.
Okay, thank you. So basically the target state is always somewhat similar to the initial state, like in the adiabatic transformation. You only want this CMs get a finite phase, a global phase that is ignorable.
Yes.
As long as you can do it either by adding HCD or dropping this extra term in equations, then you're fine.
Yes, I mean, you can only, I mean, at a finite time transformation, you cannot drop this term. Because, I mean, this term is basically proportional to, as we showed here, this term is proportional to the time derivative of the Hamiltonian. So
but the target state is already the CM up to some phase factor.
Yes, exactly. Yes. And you need to somehow get rid of this term that couples you to the rest of the energy eigenstates in an uncontrollable way.
Okay, thank you. And another question is that this gap that you are talking about, it is also changing in time. So I have to make sure that at all times it's not very small.
Yes, exactly. Actually, that's also another quantum control method. So the thing is, so even if you have a level crossing, when the gap closes and then one of the energy eigenstates changes, the energy of one of the eigenstates becomes larger than the other, or there's an energy level crossing. If you are doing things slowly enough, you always follow the same energy eigenstate. So, for example, we have these adiabatic passages. such that you can invert populations and all. So if you would like to do that also, I mean, if you would like to invert the populations, if you that's also fine. You can also do it in with an adiabatic method, and you can even fasten that with this counter-diabatic driving term. However, as I said, it depends on what you would like to control in general. That would be my answer, I guess.
Okay, I understand. Do we have questions from the audience? In the chat, I don't see any, but if you have further questions, you can email Barış.
Yeah, anyone can email me. Maybe let me write it. Sorry, of course there is no.
And maybe your lecture notes are accessible also.
Yes, I will put them in Drive after I complete the lecture notes of tomorrow, also together with some references to papers, basically.
And no homework for today?
I guess I took a bit longer than I was expecting, so therefore let's skip the homework for today. I will give a couple of homeworks tomorrow.
Okay, then thank you, Barış, again.